Your app works, it's evaluated, and it's guarded. But once real users hit it, 3 new questions decide whether it survives: where is the time going, where is the money going, and what exactly happened when something broke. This episode is about seeing inside a running LLM app. We'll build a tracer, meter every call's tokens and cost, route tasks to the cheapest capable model, and measure latency the way that actually matters. You can't improve what you can't see. In episode 14 we wrapped Atlas in guardrails. Today we make it observable. A demo you run by hand needs none of this. A service handling thousands of requests needs all of it. We'll cover 3 things: tracing, so you can see where time goes; cost, so you can see and shrink the bill; and latency percentiles, so you measure the experience your slowest users actually get. Let's start with tracing. Here's the mindset shift. In a demo, you run the thing once and look at the answer with your own eyes. In production, your app answers thousands of times a day and no human watches any single call. So when a user reports that it was slow, or your invoice spikes, or an answer was wrong, you can't reproduce it by staring. You need the receipts the system recorded at the time. That's observability, tracing, metering, and structured logging, designed in from the very first day rather than bolted on after the incident. When an agent call takes 4 seconds, you need to know which step ate them: retrieval, the model, a tool. The answer is a trace, and a trace is just a tree of spans. A span is one unit of work, a name, a start and end time, and some attributes like tokens, cost, or model. Spans nest. The agent span contains a retrieve span and a generate span. The generate span might contain a tool call. Render that tree and you instantly see where the time went. This is exactly what LangSmith and OpenTelemetry do at scale. Over the network, we'll build the local version so it's never magic. Here's the whole data model. A span holds a name, a start and end timestamp, an attributes dictionary, and a list of child spans. The MS property gives its duration. We track the currently active span in a context variable, which is what lets child spans automatically attach to their parent across the call tree, even across async boundaries. That's the same trick the real tracing libraries use. Instrumenting code is now one line. With traced, open a span, do the work, and the context manager times it and pops the stack on exit. If there's already an active span, the new one nests under it. Wrap your retrieve step, your generate step, your tool calls, and you get a complete waterfall for free. Observability becomes a wrapper around your code, not a rewrite of it. Run it, and the trace prints as an indented tree, the same waterfall you'd see in LangSmith, but local and free. Each line shows the span's name, its duration, and the attributes we attached, token count, and which model handled it. At a glance you can see the shape of the work and where the milliseconds and tokens went. In production you'd ship these spans to a backend. The concept is identical. You won't hand-roll a tracer in production, and you shouldn't. LangSmith gives you a traceable decorator that captures spans automatically and ships them to a dashboard with search and replay. OpenTelemetry is the vendor-neutral standard that feeds Jaeger, Datadog, or Honeycomb. But every one of them is the span tree we just built, plus a network hop and a UI. Knowing the shape means you'll use those tools fluently. Tracing shows time. Now let's see money. Cost is the one number in an LLM app that's fully deterministic. Given the token counts and the prices, the dollar figure never varies. So let's make it visible on every call. Keep prices in exactly one place. Here are the 3 cloud tiers, quoted per million tokens, input and output. Notice output costs about 5 times input across the board. That asymmetry is why long answers, not long prompts, are usually what's expensive. The cost function is pure arithmetic, tokens times price. When prices change, you edit one table and nothing else in the cost path moves. Sit with that 5-to-1 ratio because it changes how you design prompts. The tokens you generate are far pricier than the tokens you send, so a rambling answer can cost more than a large block of retrieved context. That gives you two cheap levers. First, ask for brevity directly in the prompt. Answer into sentences is a real cost control, not just a style choice. Second, cap the reply with max tokens, the hard per call spend limit we met back in episode 1. Shorter answers are usually better answers and cheaper ones at the same time. The exact token count comes back on resp.usage after a real call. But you often want a number before you spend to budget a prompt or pick a model. TikTok gives a free, offline estimate, accurate to within a few % for English. It's not Claude's exact tokenizer, so treat it as a planning figure. For the actual bill, always trust the usage field the API returns. Here's the instrument we bolt onto Atlas, a decorator. Wrap any function that returns a result with token counts, and every call is timed, costed from the price book, and appended to a shared ledger. The wrapped function stays oblivious, it doesn't know it's being measured. This is precisely what LangSmith's traceable does, minus the network. One decorator, and your whole app becomes accountable. While you are metering, decide what to record. A good per call log line carries a request ID and user ID so a single complaint can be traced to a single call, the model and token counts and cost, which is your money trail, the latency and the outcome. Did it succeed, refuse, error, or get blocked by a guardrail? And log a hash of the prompt rather than the raw text, so you keep privacy by default, exactly as we argued in the guardrails episode. These fields are what let you answer what happened to this user at this time weeks later. Here's the same fixed call, 1,000 tokens in, 500 out, priced across the 3 tiers. Haiku costs a third of a cent, Opus costs over 5 cents, 15 times more for the identical request. When you are serving that call thousands of times a day, that multiple is the difference between a sustainable product and a frightening invoice. Which raises the obvious question, does every request really need Opus? Most requests are easy. A few are genuinely hard. Paying Opus prices to answer what are your pricing tiers is pure waste. The fix is a router that sends each task to the cheapest model that can still handle it. A small scorer rates each task's difficulty, then routes. Easy lookups go to Haiku, the default workload goes to Sonnet, and only the genuinely hard reasoning climbs to Opus. The scoring is deliberately rule-based, free, instant, and explainable. You can add a tiny Haiku classifier for the gray cases later, but simple rules handle the obvious 80% for zero cost and zero latency. The router reads to cheap signals, how long the prompt is, and whether it contains reasoning verbs like prove, derive, or architect. A long or reasoning-heavy task goes to Opus. A short lookup with a verb like define or list goes to Haiku. Everything else takes the safe Sonnet default. It's a dozen lines, fully deterministic, and you can read off exactly why any task was routed where it was, which matters when you are debugging a bad answer. Run 6 representative tasks through the router and the decisions are exactly what you'd want. The 2 trivial lookups go to Haiku. The 2 ordinary support questions take Sonnet. Only the prove this and architect this tasks reach for Opus. Each decision is transparent and free. Now let's see what that does to the bill. On this small batch, routing came in 31% cheaper than sending everything to Opus, and it would have been even cheaper against an AllSonnet baseline for the easy tasks. 31% of your largest variable cost, with no loss in answer quality, just by sending easy work to cheap models. Multiply that across millions of calls, and the router pays for itself 1,000 times over. This is core applied AI engineering. One number left: speed. And here the trap is the average. The mean latency is the most comforting and most misleading number in your dashboard. Let's measure speed the way users actually feel it. Imagine 95 calls return in 200 milliseconds and 5 hang for 4 seconds. The average looks healthy, yet one user in 20 is having a terrible time. That's why you report percentiles instead. The P50th, the median, is your typical call. The P95th is your slow tail, the number you put in a service level agreement. The mean smooths over exactly the pain you most need to see. Percentiles are simple to compute. Sort the latencies, then pick the value at the rank corresponding to the percentile. This nearest rank method needs nothing but the standard library. We summarize P50, P95, P99, and the max. Capture a latency on every call, the metered decorator already does, and you can compute these continuously and alert when P95 drifts past your target. Here's the picture. Most calls cluster on the fast left side, but the distribution has a long right tail. The median sits in the fast cluster and looks great. The mean drifts right, pulled by the tail. And P95 sits way out in that tail, the honest measure of your unlucky users. Optimize for P95 and everyone's experience improves. Optimize for the mean and you are polishing a number nobody actually feels. These are real durations captured of 12 live model calls. The median is just under 3 seconds, the typical experience. But P95 is over 9 seconds. One call in 20 took 3 times longer than the median. The mean, at 3.5 seconds, quietly buries that 9-second tail. If you only watched the average, you'd never know some users were waiting that long. Percentiles make the pain visible. Once you can measure speed, you can attack it. Cache repeated prompts. The fastest, cheapest call is the one you never make. Use prompt caching for a fixed prefix, as we saw in episode 4. Stream tokens so the user sees output instantly, collapsing perceived latency even when total time is unchanged. And remember, the router buys speed too. Haiku isn't just cheaper, it's faster. Cost and latency improve together. One last habit. A beautiful dashboard nobody looks at won't save you, you find out from an angry user. So turn your best metrics into alerts. Page yourself when P95 latency crosses the threshold you promised, when cost per hour spikes above its normal band, or when the error and refusal rate climbs. Notice that every one of those alerts is built from a number the metered decorator and the logs already capture. Dashboards are for investigating after you are paged. The alert is what gets you there first. Recap. We made Atlas observable, a tracer that shows where time goes, a meter that turns every call into real dollars, a router that cut cost by 31% with no quality loss, and percentile latency that exposes the tail the average hides. This is the difference between an app that surprises you with its bill and its lag, and one you run with confidence. Next episode, we package all of this and ship Atlas as a real streaming API. See you there.